This video is about connection design and capacity ratios and how we use them in Comosys. So the first thing which I want to mention regarding this is that there are two ways to work in Comosys regarding connection design, and one is that you work in an unlocked model. And when you work in an unlocked model, you have all the analysis results available, all the load combinations, all the load cases available for you. And then when it is trying to design a connection, it can go through the load cases and load combos one by one. But this one can have a certain this one can create certain issues, this way of working, because you're exchanging models between the engineer and the detailer, and the detailer sometimes doesn't want to work with the unlocked model because they want to enter lots of new elements and this and that, and the unlocked model will then not allow that. So a better and more practical way of working around this limitation is to actually transfer the forces, the internal forces, the forces which will govern the connection design. I should put it like that. So you might have hundreds of load cases for floor beams, load combinations, but only the maxima will govern the design of the floor beam connections, for example. And what you want to do is somehow transfer the results of these load combinations into the members before you unlock the model. And before you unlock the model, if you do that, then you can continue connecting and designing the connections even after you have unlocked the model. Now, in steel structures, your beam to column connections can either be simply supported or hinged connections, or typically, or they could be moment resisting connections. And in Comosys, the macros which design themselves or which suggest a design for you, if the beam is connecting to a column in a moment resisting way and there's no hinge, then Comosys will not use the internal forces, but rather it will use the capacity of the member to design that connection. And this is normal practice also, because you don't want, especially in seismically active areas, your structure is going to be pushed to the limits, and you want your moment resisting connections to be designed according to capacity rather than load. They're actually going to touch the plastic capacity in seismically active areas. But as far as the floor beams are concerned, almost 99% of the times, they're a different story. There you have a case in which you don't want to design according to the capacity of the beam, and like we all know, floor beams are typically not connected in moment resisting way, but they're hinged connections. So the primary forces in most cases are your V22, the vertical shear at the ends of the beams. And in some cases, there might be some V33 as well. And in some cases, there might be some axial load in the beams as well. But the point being that these are not designed to capacity, because if they're designed to capacity, you will get unnecessarily high number of bolts or very large, very, very thick plates or very large weld sizes, which is not practical. And the reason for that is that the realistic forces inside them are actually extremely small, in the sense that, for example, a beam as big as this might have a force of just maybe a shear force of maybe just say 20 tons at the end of it, and 20 tons would with the kind of bolts that we have these days would require maybe just 4 bolts. But a beam as high as this, as big as this, which is say a 2-meter high beam, it's going to be the moment is going to dominate as far as the section design is concerned. That's why we have this, or some deflection criteria might be dominating. It depends on the span and all. But unless it's a very, very short beam where the shear dominates, more often than not, perhaps more than 90% of the cases, more than 95% of the cases, you will have reasonably small shear loads at the ends. And if you were to do a design according to those shear loads, you will get a very small number of bolts, maybe it's 3 or 4 bolts just to connect this huge beam. But this is also a practice which is avoided in steel structures. There's a typical, I mean, you would typically want this beam to be like maybe about half full of bolts or something like that. So these are the contradictions which we face, that if we just convert the forces from the analysis into this beam and let's just design directly according to those forces, you end up with something which you don't like. So this is something I just wanted to mention at the beginning. But what I really wanted to say was that what you want to do is you want to transfer your forces from your load combinations into the beam first, and then look at those forces and see if they're extremely low. I mean, they could be as low as 0.05% or 0.05 of the shear capacity, 5% of the shear capacity. So in those cases, what you want is you want to increase that number to some sort of a minimum. And you want that minimum to be, say, of the order of half the capacity or something like that, or 0.4 the capacity or something like that. And you can do those kinds of things in Comosys. And I will try to show you the steps through which we go and how the macros will behave according to. Now, the first thing which I want to explain is that if you were to, say, double click on a beam and go to the detailing definitions tab, you will see these two variables over here. One is called the shear capacity ratio, and one is called the axial capacity ratio. And by default, they're 0, unless you fill those numbers up with a special command, which I will show in a second. But whatever, so if I were to write 0.3 over here, what that would mean is that when I went through all the load combinations and I looked at the V22 and the V33 variables, and then I converted them into the equivalent shear capacity of this member, then the maximum or in the case of V22 and V33, it would be the square root of the sum of the squares. Usually the V33 will be very small. V22 will be dominant, maybe 90% or 95% of the load. But in any case, the combined shear forces compared to the axial through the shear capacity of this member is just about 0.3 or 30% of the shear capacity of this member. So I want my, let's say if I'm using a fin plate or a beam to beam end plate or a stiffen end plate connection or whatever, I want this member to be designed according to 30% of its shear carrying capacity. And similarly, this beam could have an axial force, and the axial force could be, say, 1 ton. And if I were to go to its analysis tab and it has a cross-sectional area, and if I take the axial load carrying capacity of this member and convert and relate that to the axial capacity, it may have, say, an axial load of 0.02% of its axial capacity or something like that. Now, if I were to double click on, say, a horizontal bracing and go to the same detailing definitions tab, this time, instead of having two numbers, one for the shear ratio and one for the axial ratio, we have only one number called the axial capacity ratio, because those members are primarily there to take axial loads. So once again, this number could range from 0 to 1, 1 being the full capacity and 0 being no load at all. And typically these numbers will be of the order of, if you look at the forces, and they could be of the order of 0.3 or 0.4 or something like that. So this is the number which will need to be filled up if you were to unlock the model. Then before unlocking the model, we need to do something to automatically fill this number up by going through all the load combinations and finding the maxima and putting a number in there so that Comosys can use that number even if the model is unlocked. And similarly, if we were to go to the vertical bracings, once again, we only have the axial capacity ratio because this element is governed by the axial capacity. And once again, the default is 0, but it needs to be a number between 0 and 1. It can be a number greater than 1 as well if you want. But primarily what it would need to be is it would need to go through all the load combinations find the maximum force in those maximum axial force in those load combinations, compare that to the area of this member and the load carrying capacity of this member, and the material of this member and all that, and then find an axial capacity ratio which will govern the design. Now, the way you tell Comosys to fill up these numbers. So let's go back to the beam example, and we had talked about this shear capacity ratio, which is to do with your V2 forces primarily, and your axial capacity forces ratios. The way we tell the program to, because our purpose is to unlock the model and allow the detailer to work freely. So before we do that, we need to transfer the forces into these numbers. And the way we do it is like we can select the whole building and press a button, but I'll do it one at a time. So let me select this beam. And what you do is you press this button over here called, if you open this menu, there are two commands over there, and you press this one, assign capacity ratio. And this is the command which will tell the program to go through all the load combos, find the maxima and this and that, and assign it to that number. So let me press that. And when I do that, it says computed capacity ratios for each element is set. So it's basically set the numbers for this beam. Let me double click on the beam again now. And this time you see that you got two numbers over here. Previously, these are both 0. And now the shear capacity ratio has been set to 0.5. The axial capacity ratio has been set to 0.078. This is a very small, actually it's not very small. This can be significant because we don't really want large axial forces in our beams. But sometimes you do have axial forces in the beams. So these can actually modify your choice of which particular connection to use. But in any case, so it's got two numbers in there. And now I can go ahead and start using I can unlock the model, for example, and connect this beam with these forces. Now, this command is a bit customizable. So if you were to open this over here and press the shift key, that'll, as you know, in Comosys, by pressing the shift key, we can get to the settings of the command. And this little dialog box opens up. And as you can see, there's a general tab, which is not really important. But these two tabs are important because the elements are generally broadly divided into two categories. They can be axial members or they can be shear members. And what we mean by that is that axial members are basically your vertical bracing, your horizontal bracing, or all types of trusses, etc. Those come under the group of axial members. And as far as the shear members are concerned, these are members in which your shear forces dominate the design, and these are beams and purlins and girts in which there are end releases, so they're connected as simply supported members. As I had said in the beginning as well, that as far as the moment connections are concerned, they're done according to capacity. So members are basically divided into either axial members or shear members. If I were to go to the shear members tab over here, you can see that there's a built-in hard-coded rule at the moment, and you can modify those numbers if you want to. So the hard-coded rule is that if the height of the beam is less than or equal to 200 millimeters, then if you find a shear capacity according to the load combinations, which is less than 0.5, let's say it's 0.05 or 0.1 or 0.2 or something, then if the height of the beam is less than 200, just assign a number of 0.5. So even if it is less than 0.5, assign a shear capacity of 0.5. Then it says if height is greater than 200 but less than 400, then assign a shear capacity of 0.6. And if it is actually greater than 400, then assign a shear capacity of 0.7. This is the default behavior. This will actually check your analysis results. And if the analysis results are larger than these numbers, then the actual analysis results will be converted and used in the capacity ratio. But if they're less, and this is what we were talking about, that in a lot of these cases, the analysis results are so small that you end up getting extremely awkward looking connections, like 2 bolts or 1 bolt or something like that. And that is something you don't want. So that for that reason, we have certain minimums which govern by default, but you can override these minimums by using this override axial capacity ratio over here, or this override shear capacity ratio. So you can, for example, say that in my selection, whatever I've done, and you can select according to height or according to whatever criteria. In Comosys, the selection capabilities are very comprehensive. So you can make your selection using selection filters, and then you can say override these numbers with say 0.35. But what this will tell the program is that overwrite it only if the actual capacity ratio is less than 0.35. Then use 0.3. If it is greater than 0.35 from the analysis, then it'll just use whatever the analysis results are saying. And similarly for the axial members also, there is a minimum value which it uses, but you can also have a capacity override. And once again, if your capacity overrides are less than what's coming from analysis, then those numbers, the analysis numbers, will be used as well. So this is a very handy and quick way of, the whole purpose of this whole thing is to be able to unlock the model without really losing anything, and to allow the detailer to continue the detailing with the analysis results saved away in the form of these compact numbers, so that the connections can be designed accordingly. Now, I want to say a few words about connection design and the basic procedures which are followed in the background, so that you understand, and then you can use you can understand the assumptions and then you use it accordingly. So, like I said, like I had explained, that we have these capacity ratios inside the members, and you can convert your analysis results into these equivalent capacity ratios. And when you actually go ahead and you do a connection, so I've created a connection over here. What it does is a preliminary design. That's what needs to be understood. What it is doing is it's a basic design. It's like it's creating a suggestive connection for you, that in all probability these number of bolts, this thickness of plate, this size of weld will probably work. What it is not doing is a full detailed code check. It's like a preliminary design. You can think of it like that. But then after having done that, so for example, right now I've made this connection, and if I were to go into the color coding, I can see that this is green. What this green is now telling me is that actually the full design check is also working out. So I need to explain this, that it might be that in the preliminary suggested design by the macro, some detailed design checks might be red. Like I said, in a lot of cases it'll be green, but sometimes when you apply the macro, it's going to come out red. Why is that? Why doesn't it always come out green? And the reason for that is that when you apply the macro, what it is basically doing is a preliminary design, not a final design. It's basically calculating approximately based on the loads that we've provided, a number of bolts, the thickness of plates, and size of welds. And the reason why I say approximately is because when you go to the codes, there are a lot of detailed ifs which it goes through. So the allowable variables, for example, the allowable shear capacity or the allowable tensile capacity of a member might have lots of different conditions, so that in this condition it is this, and in that condition it is this, and it's modified by 10% or 5%. So in the initial application of the macro, those detailed checks are not done, but approximate preliminary checks are done, and more or less final, we can say, connection is applied. But then when you actually go ahead and you create your design report, which you can do by saying M and going to this M enter and going to the macro and saying show me the default connection report. At that point, you actually go and create all the program goes and does all the code related detail checks. And in this one, if the preliminary design was incorrect or insufficient at some point, you will see some things failing at this point. And so this is the basic idea of the preliminary design and the final check. What you see in the report is the final check, and this is the detailed one. And this is what you need to understand. So whenever you see something red, when you apply the macro and the color coding is red, then you have to go inside and find out why it is red. and then go back to the macro and make some appropriate changes, because the preliminary design does not work 100% of the times. So now a question would arise that if upon the initial application of the macro, it is only doing a preliminary design, then what exactly is it checking and how is it making the preliminary design if it is not going through all the code checks, but it is only going through a rough rule of thumb, or not a rule of thumb, but a rough estimate of what the number of bolts should be, what the thickness of the plate should be, and what the size of the weld should be. What exactly is it doing? And to understand that, let's take this example. This is for a simply connected beam. It'll just do 2 or 3 major checks. Like what it'll do is, let's say the load on the shear force on this is, say, 5 tons. So it's going to just go and check. It's going to take a rough guideline number for the shear capacity of these bolts. And the reason why I'm saying a rough guideline number is because when you actually go to the code, like I said, it might dictate several conditions. That in this condition, you modify it by 10%, or you increase it, or you decrease it, or you take a different value. But in the preliminary design, it doesn't go through all that. It'll just take a suggested allowable shear value for the bolt and do the basic number of bolts check. Similarly, for the plates, it's going to do a very simple bearing check. And for the welds, it's going to do a very simple weld strength check. And if the bolts are in tension, it's going to do a tensile check. So the very simple, what you typically do by hand, very simple back of the envelope kind of calculations. But where does it take these allowables from? Because obviously the code has several ifs, but in this case, we're talking about a simple allowable. So for that, what we have to do the preliminary design only. By the way, let me repeat that. For the preliminary design, we have something called the material constants file. And this is important. So where does this material constants file reside? Let's go to our preferences directory and scroll down to M. And we have this file called material constants. And if I were to double click on this and maximize it, you will see that it has a certain format. And the format is actually very simple. So all these are the headers. These are the columns. So you have your code. You have the name of material. So let's say the name of material is ST37. And then you have a code, a design code. And then you have the yield value for that material given in that code. You have an ultimate value given in the code. You have a value of the bending, bearing, punching, the E value, the new value, the tensile strength, the axial strength. These are all allowable, guideline allowable numbers, right? If you actually go to the code, they might have, so for example, if I were to take this ST37 AST, it says that the allowable shear strength is 70.5, whatever the units are. Now, if you go to the code, it might have lots of ifs. It might say that in this condition, in this case, it is 68.7. In this case, it is 75. In this case, you divide it by gamma. You multiply it by that factor, or this and that. But this is a back of the envelope kind of a suggestive calculation, which you can also, by the way, modify these numbers so that you can have slightly over-designed connections as well in the beginning. So for all these values, and most importantly, these values for the allowable tensile strength, allowable axial, allowable shear, allowable slip. This is also for slip critical bolted connections. For the welds, you have allowable fillet strengths, allowable butt weld strengths, etc. If it's concrete, you have allowable punching related values. So these are all guideline values. Like I said, they won't be used in the report. They will be used in the preliminary analysis, which the macro quickly does and applies a macro for you. So why are some of these numbers 0? Because these materials, so for example, you have steel on the left-hand side. All these are steel, but then you can get to other areas of the file where, for example, the rebar material might be over there, and the rebar material will have its own allowables. And then you can go to a point where you have your bolts over here, for the 4.6, 5.6, 8.8. So for all these, so for some of them, so for example, these last numbers are always 0 because these are weld-related strengths. And if you go down further, maybe we can find some, yeah, okay, over here we have the electrodes, E60, E70 electrodes, and in these electrodes we have these allowables filled up for us. So the basic idea of this whole file is to provide allowable strength values for these materials for various cases like axial, shear, slip, fillet weld, butt weld, punching, depending on what the material is. So the program will go to this file, just pick up this randomly, or not randomly, but suggestive number, let's say, preliminary design number, and use that design number to do a very quick back of the envelope kind of design. So let's say you're allowable for ST37 for shear is 70.5. This is about 0.7 tons per centimeter squared. So if that is the number, it's going to multiply that by the shear area of that beam, and it's going to find out the capacity of that beam, and then it's going to say that whether the number of bolts are working for that or not. And like I said, these numbers will not appear on your reports. These will only be used in that preliminary design, which the macro quickly does to find an approximate number of bolts, thickness of plates, and weld sizes. Now let's actually do a very, very simple analysis by hand so that we can get a feel of how it uses the material constants file. So here is a beam which is being connected, and if I were to double click on that, I can see that I've taken 0.4 or 40% of its capacity, shear capacity. Now the question is, what is the shear capacity? So if I go to the analysis tab, we can see that the shear area is 11.2 centimeters squared. This is in millimeters right now, so it's 1120. That's about 11.2 square centimeters. And for each centimeter squared of area, it needs an allowable value for the shear allowable value. And for that, we will need to go to the material constants file, which we just checked. So just remember this 11.2 square centimeters area. And let's go to the material constants file again. And in the material constants file, this is the material ST37 of that beam. And if you notice, there are 4 lines for this material and 1 line for each chord which is supported. And if we go in there, and I'm right now doing according to the ASD, and in the ASD standard, I have, we have this file is telling me that the allowable shear is 70.5 newtons per millimeter squared over here. This is the number. You can change these numbers. Like I said, you can lower them if you want to. If you want to create a slight over design or whatever, you can modify these numbers. These are entirely used only for that initial preliminary design. So it is 70.5 newtons per millimeter squared. Let's just take G to be 10. So this is about 0.7 tons per centimeter squared. So if you remember, it was 11.2. The area was 11.2. And if I were to multiply 11.2 by 0.7, for example, it's about 7.8 tons. So the shear capacity of this beam is about 7.8 tons according to this preliminary design. But beyond that, I'm actually taking only 40% of that, of the shear capacity. So if I were to multiply 7.84 tons multiplied by 0.4, I will get something like 3.13. So basically what I'm telling the program is that you roughly take about 3 tons of load, 3.13 tons of load, and find the number of bolts for that. Now, if we were to go to the bolts, for example, over here, which are going to take the shear load, and check the material of the bolts, the material is 8.8. And once again, if I go back to my material constants file and scroll down to my bolts this time, I have my 8.8 bolts, the same standard as the one before. And for this, the allowable shear is about 2.25 tons per square centimeter. It's a lot higher than the other material, almost 3 times higher than the other material. But like I said, once again, these values are in your hand. You can modify them just to produce a better initial preliminary design if you wanted to. But there's a certain reason why I'm going through this in a detailed way at this point. So this is about 2.25, and if you remember, it was our load requirement was just about 3 tons. So one single M16 bolt, those were M16 bolts, by the way, and the area of a single M16 bolt is about It's about let's say it's 1.6 into 1.6. It's about two. Sorry, let me just calculate that again. Yeah, it's about 2 centimeters squared. So and the allowable is about 2.25 tons for each centimeter squared. So 2 multiplied by 2.25, and I know that even a single M16 bolt takes about 4.5 tons according to these numbers. These are just, like I said, preliminary numbers. But a single bolt is taking 4.5 tons. But the total load which I want to take is about 3 tons. So it's not going to put one bolt, it's going to put one bolt on both sides. So easily, even a single row of bolts will be able to take the 3 tons which are coming to this beam. So the two bolts put together actually have a capacity of taking about 9 tons of load, but the load is only 3 tons. But now I'm going to show you something where this preliminary design fails, because this just does a very simple check of basically dividing the load by the bolt's allowable shear. For example, it doesn't do a block shear check, for example, which can cause other different type of failure. It doesn't do that in the preliminary, but it will do that in the final report, and that's where you're going to find out. So if I were to go and double click on this beam and increase this shear capacity ratio by say to 0.5. Now, this is a very slight increase as far as the load. Our load will probably go from 3 tons to say 4 tons. So it should still be green. But when we do that, we see that the thing turns, the detailed connection turns red. And this is telling me that the preliminary design which I had done wasn't sufficient and something is wrong. So I need to go in and check. So what do? I just select any member. I say M, right click, go to the macro, go to my connection design report, open up the report. And when it opens, I can just scroll down and see exactly what went wrong, and there'll be a fail somewhere. And don't bother about these informative ones. They're not structural checks, just giving you information. And so things are passing, but over here, okay, so just like I thought, this bolt group shear resistance is failing slightly, right? And this sort of, although my bolts can still carry the shear very easily, but this group shear resistance check, which was not part of the preliminary design, has caused a problem. So if I go further down and see if anything else is failing as well, the other things are seemingly okay. And this usually happens when the loads get concentrated around a single line of bolts. And the easiest solution is just to increase the number of bolts to 2 rows or 3 rows, and then this check will easily be solvable. So what we can do is we can let me close this report. We can go into the macro, and instead of the automatically calculated single row of bolts in the preliminary design, I can make it two rows of bolts, for example. And when I do that, immediately now my connection turns green. And now I can actually go back into the report again and open it once again, and see that this time that bolt group check, which we just saw failing over there, yeah, here it is. So this one was failing previously, but now with the modified parameters, this has passed. So to summarize, I hope I've been able to express why the macros don't turn out green all the time at the very first attempt. Because in the first attempt, the first cycle is basically a preliminary design cycle in which a very simplified design is done based on the material constants file. And like I said, you can go ahead and you can modify the numbers in there. You can lower them. You can lower, for example, the allowable bolt shear stresses, for example, actually let's say 20-30% below the standard values taken. And that what that will help you with is that most of your initial preliminary designs will turn out to be green, right? But in any case, in the final analysis, once you actually create the report, you can actually see all the detailed checks done over there. So to repeat, it's a two-step process. The first step is merely a preliminary design, which is based on these numbers in the material constants file. And these numbers are, like I said, they're close to the numbers suggested by the standards, but they're not exactly the same because the standard for the same allowable can have 10 different values. So we don't have that option of creating putting all those numbers in there. But these are all suggestive allowables, allowable for axial, allowable for shear, allowable for slip, and this and that. But what this allows Comosys to do is a very quick initial design for you. But then once you create the report, then you can see what the actual check for that report is. And this two-step process will make you understand how the design of the connection works. So now let's do a slightly different example. I have this slightly larger beam, and initially I've set it to 0.1 of the shear capacity, and it's green. So all the code checks are passing. Let me increase this to 0.2, and it's still passing. Let me increase that to 0.3. And this time you get a little more bolts, but it's still passing. Let's increase that to 0.5, and it increases the number of bolts according to that load level, and it's still passing. Let's make it 0.6, and that's still the same number of bolts is enough. Let's make it 0.8, and this time the number increases, but it turns red. So I need to find out. So what this is telling me that as far as the preliminary design was concerned, I had suggested a few values and they were working fine. But at this load level, some of the detailed code checks are not working out. And I can go back into my macro at this stage and go to my connection design reports and open up the report. And if I scroll down, I will see that generally the bolt checks are passing, but there's a plate block shear, end plate block shear, which is failing, and the plate. So basically, because in the preliminary design it only checks for the bearing of the plate, so that's okay. But this plate block shear related checks, since they were not done in the preliminary design, and in the detailed design they come out. So now what I need to probably do is I need to go inside and change the end plate thicknesses over there. So let me go and change the default thicknesses which it has used, doing only the preliminary check. And if I do that, then once again, even at this level, it turns green. And let me see if I can take it all the way to the full capacity. And apparently I can. So with these 6 rows of bolts and with the 12mm thickness plate, I can design this connection in this way. Now, there is one final thing which I want to talk about, because that can lead to some confusion, and that is that there could be a conflict between. So, if you remember, I said that by changing these numbers, you can modify the preliminary design suggested by the macro. But then we had also discussed elsewhere that what you can do is you can create your company presets for the various profile sizes, and you can automatically apply those presets. So we had done an example in which I had created 3 presets for the fin plate connection, and this is the preset for the IPE 400 one. And if you remember, these presets are automatically applied if you have the automatic preset override file, which we had discussed. So let's go to the fin plate connection macro. Yeah. So this one, we've entered the 300, 200, 400 automatic preset files, the MPR files, which we have discussed in another video. So that's telling Comosys that whenever you see an IPE 400 section, you go to that company preset and you apply that preset over here. So this is what it's going to do by default. Now, if you were to come in and double click on this IPE 400 section and go to the detailing definitions tab and try to modify this shear capacity ratio, let's say you want to make whatever so right now it is not designing according to this. Right now it is just putting the company presets, because the company wants that whenever you see an IPE 400 profile, this is the way you connect it. So the preliminary suggestive design is kind of turned off right now. So if I were to, for example, go in and make this 0.3, nothing's going to happen on the screen, because what it's doing is it's checking the 0.3, but then it's saying, okay, this is an IPE 400 section. I have an IPE 400 preset as well inside, and the company or automatic presets have also been set up. So I will just use that. So if you wanted to kind of override those company presets for a moment, what you would do is you would go into your macro, and in the presets tab, you would turn off this flag over here, which is override the defaults which are used with the preset files. So if I were to turn this off and say, okay, and now if I were to go in and make a change in the detailing, say bring it back to 0.1, okay, the reason that didn't work is because the macro already has loaded up those defaults, so I need to clear those defaults as well. Let me go in and clear those distance related defaults like that. Yeah. So now it is actually going in and it's doing some sort of an analysis, and now it's modifying the if I were to increase it further, now it's changing the bolt diameter, and right now it's doing that preliminary design which it does based on the material constants file and the load level. But if you have turned on these presets, then what it will do is it will basically go and look for your it's going to basically look for your automatic presets and will try to apply those automatically as your company standards.